Hello, good morning. Can you all hear me?
Yes, sir, we can hear you, sir.
Okay. I can see about 11 participants. How many of you are there in the batch? Ten participants are there.
Normally around 14, I think so.
14. Okay. Do you think we have to wait a little bit more or we should start?
Shall we wait for another 5 minutes and see?
Okay. So then by 5 minutes, let's see.
Yeah.
Okay. 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 Good morning. I think we can start now because I can see now about 16 participants are there. Can you all hear me clearly?
Yes, sir, we can hear you.
Can hear you, sir. Good morning.
Right. Good morning. So please enter your name and your number in the chat box, okay? Because that will register your attendance. That must be done in the chat box. Your name and your registration number. Everybody should do that. Right. Okay. So I think in this unit you have been already taught about delivered about some aspects on the earth and its processes, right? So what I was asked to do under this course unit is about the earth structure, right? Earth structure. So we will start with the facts on the earth structure and its internal structural features, and then we can little go deep into the some processes, earth's processes. Okay, so but before that I just want to know about the backgrounds of your each of you, right? So shall we start saying about your background? I mean, in which field you have studied in a basic degree? So maybe I can start with I mean, according to the list I will ask you. So can you please unmute and let me know? Okay. First, Udeshika Madhushani.
My basic degree is Information Technology and Management.
Information Technology and Management. From where you studied? I mean, the degree?
The University of Moratuwa, Faculty of IT.
So why did you want to go in the gemology field?
Yeah, I like gemology. I like gemology, and I'm interested about that. That's why I selected this course.
Currently, you are studying. You are working at where?
No, I'm not working yet.
Okay.
Uh,
You just graduated or what?
yeah, just graduated.
Okay.
August.
Then thank you. Then Shashi. What is that? The surname? Sorry. Yeah, Sashi. Are you there? Yes. Tell me about your field. I mean, the study area. Sashi Malalasekar, isn't it?
Yeah.
Yeah.
Yeah. I'm Shashi Malalasekara. I have a degree from Sri Jayawardhanapura University, chemistry degree. Then I have followed Gemmology Diploma in Gemmology Association, DGMSL.
Yeah.
I'm a member of that association. Now I'm working at Gem and Jewelry Research Institute as a director. I'm a board member actually.
Okay. Right. I was also a board member some time ago.
Oh, really?
JGRTI.
Yeah.
Yeah.
I'm since a year actually.
Your degrees from which field?
My degree is from chemistry.
Right. Then, thank you. Then,
Okay.
Suprara. Can you hear me?
Yes, sir. Good
Yeah.
morning, sir.
Good morning.
My basic degree in biological science in Southeastern University.
Mhm.
I am following chemistry, bio, and earth science mainly.
Okay. So you are interested in gemology, and where are you working at now?
Not working, sir. I am interested geology
Okay.
subject.
Okay. Right. So okay. Thank you. Then Kasun Madivila.
Good morning, Professor.
Good morning.
Yes, I did gemology,
Mhm.
Gemological Institute of America.
Okay.
So also I'm running my own gemological laboratory.
Okay.
Yes,
Right. Where is it?
it's in Beruala, Colombo, and Ratnapura, and also in Bangkok, and also supposed to start in China as well.
Okay. Okay. So you are in the field of business, gem business, right?
Yes, yes, doctor.
Okay. You have a lab as well?
Yes, lab. Yes, gemological laboratory.
A laboratory. Okay.
Yes,
Are you doing any diamond related things, diamond grading or something?
yes, doctor. So I studied the diamonds as well.
Oh, okay.
Yes,
Okay. Right. Thank you. Good.
thank you, thank you.
Then we'll move to Dasit Kamil Vijay Tilaka. Yes, Dasit.
I did my degree at SLIT, BSc in Civil Engineering.
Okay. Now, where are you working at?
I am doing businesses in several industries, and I have a shop, and I do another business in supply.
Okay.
Supply.
Right. Mhm. So then we'll move to Nishanta Patirage. Nishanta, can you hear me?
Yeah, I can hear you. Can you hear
Okay.
me?
Yeah. Which field you are
Yeah,
from?
I'm Nishant Paturega. I'm graduated from University of Sri Jagadhanapura
Yeah.
to the real estate management and valuation.
Uh-huh.
And from other side, I'm a fellow of chartered accountant. I'm working as a CEO of a Sri Lankan company.
Sri Lanka which?
Sri Lankan company. I'm
Okay.
affiliated with the Homeland Group for company.
Okay. Uh-huh.
And I'm diploma holder from GASL, and
Uh-huh.
as an executive committee member and a treasurer there. And I'm
Oh,
into the gem business, and practically I have a shop actually. I'm dealing with the international market.
okay, right. Thank you very much. Then we'll move to Samanjit.
Yes, sir. Good morning.
Morning.
My basic degree is mathematics. I have done a special degree in mathematics at University of Colombo.
Uh-huh.
After that, I joined Sri Lanka Customs, and I'm working for as a superintendent of customs in Sri Lanka Customs.
Uh-huh.
Now I have been working at gem and jewelry appraising branch also in customs, and I have followed the certificate degree in certificate diploma in University University of Moratuwa and GSL as well, sir.
Okay. So you are from customs. There are several custom members who are usually participants of gemology MSc in the previous years. Do you know them?
Yeah. No, and Balage,
Yeah.
Dr.
Even before that, Ajit Sirivardhan.
Ajit and Shanta Priya.
Yeah.
Yes.
Even Ajit is a resource person in this course.
Yes, I know.
Yeah. Okay, right. Thank you. Then we'll move to Samita Liyanage. How about Samita? About your background?
Good morning, Professor.
Good morning.
I am actually I have done my basic degree in logistics management in Plymouth University. So then I have done diploma in gemology in Gemmologists Association, and I have done CIMA as well.
Okay.
So currently I am running my own laboratory in Colombo, and I'm the secretary of Gemmologists Association.
You are a secretary there. Okay.
Yeah, exactly.
Right. Okay. Thank you.
Thank you, Doctor.
Yeah. Then I cannot see the correct name. It says Zen. Zen. Your full name is not there.
Hello. Good morning,
Hello.
Dr. Sir.
Yeah. Good morning.
I have a basic
Your name?
degree.
Your name?
So my name is Dank Stuhlinger.
Okay.
I have a basic degree in BSc Business Administration, Yapura. Then I followed a certificate course about gemology at Geological Institute Training and Research Center.
Okay.
Kadwala. Then I interested about gemology.
Yeah.
And hoping to do the business as well.
Okay. Right. Yeah. Thank you. Then we'll move to somebody called iPhone. Your name? Can I know your name, please? Can you hear me? The one who is connecting with an iPhone.
Hello.
Hello. Yeah.
Hello. Good morning, sir. Yeah.
Good morning. Your name?
I'm Binar, sir.
Okay.
Yeah. I did my basic degree in management in University of Colombo, and after that I moved to business field for gem field, and I did diploma certificate course in Moroto University.
Okay.
Now currently I am doing gem business.
Okay.
Yes, sir.
Right. Okay. Thank you. Please later in your Zoom account, can you please change your
Yeah,
user?
I have already logged in from my laptop.
Okay.
I think
Maybe
I have mentioned my name. So.
Okay. But it displays as iPhone. That's why I thought.
Yes. Yeah, that's the reason.
Okay. Thank you. Then we'll move to Kanishka Herat.
Good morning, sir. My BSc I've done in software engineering from Staffordshire University, UK, and then I also did my MBA from University of East London, UK. Currently, I work at Fonterra Brands Lanka as the demand planning manager. The reason that I've selected this course is my personal interest, not only in gemology but in minerals as a whole.
I see.
So yeah.
Okay.
Thanks.
Right. Good. Thank you. Then Udaya, can you hear me?
Good morning, sir.
Good morning. Yes.
So I have followed geography special degree from Peradeniya.
Geography. Okay.
Yeah. Now I am doing my MPhil degree at PGIS.
Okay.
After finishing my bachelor degree, I worked as a trainee at Lanka Mineral Science. Now I'm continuing my research.
Okay, you did the research with Mr. Ashwin.
Yeah.
Okay. I know. So you are taking part in this course as a coursework requirement, right?
Yes, sir.
Okay, right. Okay, thank you. Then let's move to Vijayanti Gulavatta.
Good morning, sir.
Good morning.
I got my degree from Chartered Institute of Marketing, UK, and also recently done a diploma in gemology at University of Moratuwa.
Okay.
And I'm interested in this subject, and currently I'm not working.
Currently where?
Yes.
Okay. So you are you just for the interest you are following this one, right?
Yes. Yeah.
Okay. Right. And we'll move to Pinara Vanyarachi. Pinara, can you hear me? Vinara,
So
are
I
you?
think he spoke on the iPhone. I think it's the same person who
Ah,
spoke
I
on the iPhone.
see.
Yeah.
Okay,
Yeah.
okay. Okay. So, but how come then? You mean both devices you are connected? Are you?
Yeah, I think so. He mentioned that.
Okay, right. Okay. Then who else? Tharindu, Danushka.
Good morning, sir.
Good
I did
morning.
my basic degree in software engineering field.
Yeah.
And I'm currently engaged in gem business.
Okay. So, what is your degree?
Software engineering.
From where?
Slate.
From Slate. Okay. So, you are just for the interest. You are following this course.
Yeah, and I'm currently engaged in gem industry.
You are already engaged.
Yeah.
Okay. Right. So then we'll move to. Did we talk with Chaturangani? Not yet, I think.
Yes, sir. My basic degree is from Mineral Processing Technology from Uva University.
Okay. Okay, right.
Can you hear me?
Yeah, I can hear you.
So I'm a gemologist now, HGL Gem Laboratory. So I completed diploma in Gemologist Association. I was a member there.
Okay, right. Yeah, thank you very much. So I think everyone we already connected, right? Is there anyone who did not talk? Yeah, I think everyone is fine now. So shall we move to the lecture then? So today I will be I will be basically doing on the structure of the Earth. So we will start with that. Can you all see my shared screen?
Yes.
Yes, sir.
So we will we will do on this Earth structure and processes. Actually, you know, the Earth is one of the planets that we have in our solar system. Can anybody tell me the age of the Earth? How many years ago the Earth was formed?
4.6 billion years ago.
Yeah, 4.56 billion years ago, right? So at that time, the Earth and most of the planetary bodies were formed. So what about the age of the solar system? Anybody knows? Age of the solar system? The initial time of formation, timing of formation. No idea? It's about 14 billion years ago. 14 billion years ago, the parts of the solar system started to form, but at that time there was no planetary formation anyway. Before a planet can be formed, there are some stages. There are some preliminary or proto stages where these planetary bodies get into accumulated by by tiny particles and some gases available in the solar system, available in the space at that time, and then only these tiny things get accumulated together and grow into a planet. So this process we call as a general process called accretion. So in this particular instance, we are talking about the Earth's formation. So the from the particles which were accumulated in actually it's in a very vacuum. It starts in a vacuum first, and then since the particles are coming filled with very tiny dense masses, there will be a gravitational field generated gradually, right? If there is a mass, there is a gravity generated. So with that, later on, time to time, these particles were accreted. That means accumulated together. We call it accretion. And the planetary bodies were formed as proto planets. First of all, they are not planets. They are called protoplanets. So we will see in detail why these are called protoplanets and all with the progress of this lecture. And for formation of these planetary materials or planetary bodies, initially there is a cloud-like thing contributing. That's what we call a solar nebula. So from the solar nebula only, these planetary materials get accreted because of the rotation, the fast rotation, and they form into a disk-like feature, right? It's like a disk. So because of the rotation, the masses are distributed along the plane of a disk-like feature, and out of that, different places at different places, these masses are get accumulated. So that's why we have several planets formed in this solar disk. So it's a kind of a process. I mean, it's a long process. It's a long process which is first starting with a giant cloud, which we call a molecular cloud. It's a very big molecular cloud, and this cloud contains some dust particles as well as some gases, or some very tiny material. And these materials first form a something called solar nebula. So this solar nebula is something like a disk like thing, and when this disk is rotating continuously, because this is rotating due to its momentum, and place to place, you can see here, like it's a model, uh, some tiny materials get accumulated, right? So they get grown themselves uh, to bigger bodies, slightly bigger bodies, and then these materials we call planetesimals, and these planetesimals get them accumulated as well. So once they get accumulated, little by little, these bodies get into a bigger shape. So these materials or these planetesimals in the solar nebula gets into accreted more and more gradually, and then they form into a more bigger uh, planetary body that is actually still not a planet. We call a protoplanet because for a planetary body to be called a planet, there are some requirements. So at this stage, still that those requirements are not fulfilled by that body. So therefore, we call it a protoplanet. That means it's a kind of a parental body for a planet, parental body. So anyway, this stage, this giant molecular cloud stage and solar nebula type of formation time is the one that we refer as the birth of the solar system. Okay, it's like 14 billion years ago. 14 billion years ago. That means more than 3 times like the age of the Earth. So since that time, these materials have been forming into such a shape that it could generate some planets at the end of this process. So we call this process as the accretion process up from this giant molecular cloud through the solar nebula to the protoplanets, and afterwards these protoplanets will also be changed into some kind of a shape which is now we have currently in our planetary bodies, most of our planetary bodies. For example, in Earth, you can see here uh, clearly some layers are separated in the Earth, but at the stage of protoplanet, you don't see any kind of layering. So this is the difference between a protoplanet and a planet. For any planetary body to be called a planet, you should have well layered structure. Okay, So this layering process we call differentiation, or chemical differentiation, because this is a chemically driven process depending on the density of materials. Actually, these materials means elemental distribution. The more heavier ones sink towards the middle of the body, whereas the more lighter ones are floating or are accumulated or separated along the marginal areas. So this is what we call the differentiation. So light objects float and heavy objects sink. This is what we call the chemical differentiation of protoplanets to make planets. So this process has taken place. I mean, initiation of this process has taken place about 4.57 or 56 billion years ago from the present. So it's actually 4,570 or 4,556 actually, 4,556 million years ago, right? So once we talk about these ages, actually these are geological ages. We call them geological ages, and we refer them according to the geological time scale. Geological time scale. So I hope some of you are familiar with the geological time scale. Is there anyone who is familiar with the geological time scale?
Because Navaratna did that lecture to us, I think a few weeks back.
The time scale, you mean?
Yes, yes, yes.
Okay, right, that's good. So in the geological time scale, you can see these different ages and different periods, epochs, and all. So you know that is a reference. That is a reference. So in normal time scale, it's a it's a very minute time span. If we consider some thousand years means historically it's important for us, but geologically it's a very young age, right? So like 500 million years. If I say the age of the rocks that you encounter in your garden, in your lands, if you see some rocks, right? Most of the rocks in Sri Lanka are formed at about 550 million years ago, right? But actually, some of them are very old. It's even 2.5 giga annums ago they have formed 2500 million years ago, right? So that is very old. But all these rocks that were formed at that time, at least 2500 million years ago or so, because ours oldest rocks are at that age, reshaped or they changed mineralogically later on. So that has happened at about 550 million years ago, right? So originally these rocks which were formed by volcanoes or some igneous or interior process that we are considering even under this course, they formed at that time 2500 million years ago, but later on they went back into the Earth's interior again and reshaped. They changed their mineralogy, right? So that is what we call the metamorphism. I think you have done the the process of metamorphism as well. Have you?
Yes,
About
sir.
rock cycle and all. Yeah. So rock cycle means that time to time the exposed rocks get eroded and weathered and then buried into the Earth's interior, and they get melted again and formed into magma, and then magma comes up to the surface and crystallizes, cools down and crystallizes new minerals. That means it forms new rocks. So this is a kind of a circle. So this is what we call the rock circle. So anyway, these protoplanets were consisting of parental materials to these are all rocks. Okay, so do you know the oldest rock, the age of the oldest rock that we have in the planet Earth? Any idea?
I have no idea.
Anybody know? Sorry.
Is it some zircon deposited in Australia?
Well, yeah, the age,
4.2 billion years ago.
Yeah, that's right. It's actually it's not the zircon, but the age was determined using zircon. Okay, the rock itself is old as it's about 4.2 billion years. That's recorded from Australia, Jack Hills, the area called Jack Hills Mountains, and we previously it was noted that some Canadian rocks, a place where we call Augusta uh, province or Augusta area. We call the rock name as Augusta gneiss. Gneiss means a type of a rock. Those rocks were also old about 4 billion years, but later on these zircons were found in Australian rocks. These were aged about 4,200 billion years ago. So actually, this zircon is a very I mean, you know, it's a gem. It's a semi-precious stone. It's a gem variety because it's a very resistant mineral. So being a gem, it should be durable, resistant, and beautiful, right? Those are the features that you need for a mineral to be called a gemstone. So zircon is also part of gem family, but it's a semi-precious stone, as you know, not like ruby or sapphire. But it's a very resistant mineral compared to other ones. And also the other feature is zircon is a sink for uranium and thorium, right? It can accumulate a lot of uranium, thorium, and lead, right? Uranium, thorium, lead. So these three elements are very important for dating rocks. Actually, all these dating techniques which we apply using the radiogenic isotopes. So you should learn about the radiogenic isotopes. Those who did chemistry must know that, and also earth science background people should be familiar with this one. Others also can learn it through the books, textbooks, and also through the internet. Radiogenic isotopes are the isotopes that decay into a new material. I mean, new element from one element to another element. For example, if you have thorium in the earth, this thorium decays into lead. That means it emits some gamma rays and change into a new element. So this element is called daughter, and the thorium, the parental material that we call parent. Okay, source we call parent. So parent daughter isotope decay means some kind of energy emission, and we can measure these elemental abundances. Actually, we call some neutron number change in these atoms. That's why they are changing into new isotopes. We can change these ratios, isotopic ratios, using some equipments like ICP-MS. What do you call ICP-MS? Inductively coupled mass plasma mass spectrometer. So basically by using mass spectrometry, we can measure these isotope ratios. By these isotope ratios, we have some formulas, and we can apply that to calculate the isotopic abundances, isotopic ratios, and also using the natural isotopic abundances plus these measured isotopic ratios, we can calculate. And also using the half-lives. Half-life means the amount of time taken for a given mass of a parent isotope to decay into half of it. That means if you had 1 kilogram of parent isotopes in a earth material, say it took about for maybe 40-50 million years to make it 500 grams. That means the parent has decayed into half. So that time is called half-life of that particular isotope. It depends on the isotopic system. There are several isotopic systems, radiogenic isotopic systems that we use to date rocks: uranium lead, thorium lead, samarium neodymium, rubidium strontium, potassium argon, like that. There are several isotopes. and that those isotopes can be used to date these rocks. Actually, zircon is a very resistant mineral, which is very good indicator for ages in terms of uranium lead and thorium lead system, mainly uranium lead system. So it gives very accurate age with an uncertainty or with an error about plus or minus even 5-10 million years. So that's a very accurate date. So we use these zircons because they are preserved. They can be preserved in rocks. So this is very important. And another important fact is this radiogenic decay emits gamma rays and all. There are different mechanisms as well. They emit a lot of heat into the Earth structure. So even today we have a lot of heat produced in the Earth's interior due to this radioactive decay, radiogenic decay by these isotopes. So actually these half-lives are not a very simple or very short span. Some are very short span, that's right, but some are about 40-50 billion years, the half-life. So that means our
Professor, can I ask one question?
yeah. Yeah.
Yeah, this we find zircons in different like areas. In Sri Lanka, we find some other Australia and all those places we find the zircon.
Yeah.
When I talk about like radio, like it's mechanism like the what's it's is there a difference on the hardness and the uh, radiology that kind of a percentage?
No, I mean, isotopic abundance and all can be different. It should be different with respect to the origin of it. I mean, the time of genesis, because until now, because zircon can be generated at any time, at 4.5 billion years ago, or even 2 billion years ago, or like that, right? So depending on their age, the isotopic ratios and radiogenic features are different. They are different, so that's why we use it as an indicator for measuring the age. But hardness does not change. Hardness is constant wherever the zircon forms. uh, Hardness is same, right? Because it's a mineral, so you have the hardness scale. According to that, you can explain any mineral, the similar mineral having the same hardness. Okay, hardness will not change because it's a mineral feature. Otherwise, if hardness is different, then we can't call it zircon, because there can be some varieties, slightly different varieties chemically, but generally the hardness is same for the zircon. Very slight change can be there, but basically it's almost same.
It has not connection with the when it was formed, right?
No, it doesn't have any connection. Yeah, only the radiogenic accumulation can be changed. I mean, the amounts of these dot isotopes and all concentration.
It's again the time it has formed, right?
Yeah, that's right. Because with time only these isotopes decay. With time only you can see different molecules are formed, different new atoms are formed. So that's why, not the hardness. Okay, so these zircon we can use to date these rocks. Actually, uranium lead system has used to date the early formed rocks in the solar system, because it's a good indicator of age, and because for this radiogenic decay, actually the systems, chemical systems, has to be closed. I mean, it should be behaving as a closed system. Is a requirement, because otherwise you can't balance the originally had amount plus to the presently available amounts of isotopes. So therefore this system should not be disturbed. Only disturbance to these systems could be like remelting like features, right? So if any rock has exposed to magma generating region again, then these original zircons or whatever the minerals there will be remelted, partly or totally, right? Partially or totally. In that case, the isotopic system get disturbed, so you can't get the actual date of its formation, but what you get is the age of that remelting event, right? The closest event that the rock was subjected to such kind of a major event can be dated then, but not the original age, because it has disturbed already the isotopic or initial isotopic system. But there are rocks which are not disturbed. Once the rocks are exposed to the surface, some rocks remain there without being subducted back into the surface unless you are in a subduction zone. So therefore, the original rocks are preserved. So therefore, we can get the initial date. So that's how these Australian zircons were also recovered from Jekyll Mountain rocks. They could report this age as more than 4 billion years ago, right? The formation of those are the oldest rocks in the Earth. So you can search in the Google, putting the oldest rocks in the world or something like that. So then you will get all these references as well. And when you have a time, so please go through their details. Okay. Right.
So I also do have a question. At the time of this solar nebula, was the sun already born?
Yeah, actually, it is the time of sun was born, because surrounding the sun only these planetesimals were accumulated. First, there should be a star formation. Okay, so star formation means the origin of the sun. So once you have a star, only you can have a solar system, right? Around a big star only you have a solar system. There are so many solar systems. We believe there are so many solar systems even in the universe. Some of them we have not traced, or we have not we have not understood yet. But there is a requirement for a big star to be formed. Uh, Surrounding to that only you can have a solar system, because there should be gravity. So sun means also mass, a big mass, a giant mass. So that attracts these planetary bodies to keep them in its attraction. So that's the reason. So the formation of the sun is the initial time of uh, star formation, that is related with the this nebula stage.
Yes. So does that mean that the sun is 14 billion years old?
Well, yeah, it should be a little younger than that anyway, because to form the sun also there should be some material, right? So then that material accumulation is actually the molecular cloud to the solar nebula stage is considered as the 14 billion years. Sun should be little younger than that. That means I don't know exactly the age, because there is no way for us to clearly measure the sun's age, because we cannot get materials from there.
Yes.
Yeah, that's the thing. But in the universe there are materials which are old as 14 billion years. That's why the maximum, considering the maximum age, scientists believe that is the age of the solar system.
Yes. And sir, what about the age of the other planets in the solar system?
Well, yeah, there are different ages, because we don't have measured the most of the ages of the other planets, because we don't have any rocks or any minerals from them, right?
Yes.
We need materials from them. That's why. So
Okay,
that's why the missions are conducted by different countries to bring the materials, like Mars mission. They try to collect rocks. Actually, importance is to collect rocks, not the soil, right? Because soil is the eroded part, I mean the weathered part of rocks. So most of the materials are decayed there. So you
probably moon also formed, I think, 4,500 years, right?
Yeah, it's almost same as age of the Earth, because it's a different process where some huge collision has happened with another body. So one piece of the Earth was moved into the space, and it was shaped into the moon by the rotation. So it's almost the same age as the Earth, the moon's age. It's not very young. It's almost same, because this collision has taken place at the initial times of Earth's generation. That's why it's just a part.
That means Earth has destroyed one long time back.
Yeah, yeah. And if you see the Earth's, the moon's composition, a lot of anothites are there. The plagioclase feldspar. It's a feldspar, dominant crustal part. So actually, at the time of this differentiation, uh, this moon has formed as a fragmented piece. Right. So protoplanets are generated first, and the feature of the main important feature of these protoplanets is they are undifferentiated. So what do you mean by undifferentiated? Undifferentiated means they are not separated into layers depending on the density or depending on the elemental abundances, right? So heavier ones start to sink into the interior. It's a because these are in molten stage at the time of formation. Even though these protoplanets, we call it a magma ocean. It's a kind of a molten iron ball like thing, right? So there are vigorous convection currents are active there. So these elements can move from place to place by diffusion, the process called diffusion. From high concentration to low concentration, they can move. These elements can move. So that's why these differentiation has taken place to separate heavier part in the middle and the lighter part in the outer side. So in the interior, in the middle of the parts, in this case, you can see this figure where I am highlighting. You have the iron and nickel rich elements. Iron and nickel. Those are the two elements, heavy elements, which are composed in this central part, which we call core. Okay, Earth's core. We call it core. And again, core can be divided into two sections, outer core and inner core, where the most interior part is very solid, but the outer part is still liquid. This solidness is because of heavy pressure acting upon these layers from this depth. So this is a very long depth, some thousands of kilometers. We'll see that later on. And this most interior part is composed of iron and nickel. So we have iron and nickel there in the interior part. Actually, that is the reason where of which the contribution to the magnetic field of Earth's magnetic field is due to this iron abundance in the Earth's interior, right? So you know about the Earth's magnetic field. So that is caused by this iron bearing core region of the Earth. And then a little more slightly lower densities, the elements, than the ones which were formed the core, like iron nickel is the core, and a little less dense material were composed this particular layer, which we call the mantle. Okay, so after the most interior part is core, and then next comes mantle, Earth's mantle. Okay, so this Earth's mantle and the next light layer to the mantle, above the mantle, is the crust. Okay, so we have crust at the exterior part, and then in the middle you have mantle, and then most interior what you have is core. So core, mantle, and crust differentiation has taken place after these protoplanets were formed. So this separation is the one that we call chemical differentiation of the Earth, or just the differentiation of the Earth. So this setting, once you have this type of a differentiated status of a planet, of a protoplanet, then you can this protoplanet qualifies to be called a planet, right? So planet, or sometimes called differentiated planets, is because of this differentiation. So basically the core is composed of iron and nickel, and then crust and mantle is composed of oxygen and silicon bearing minerals. So actually they are silicates. You will learn details of these silicates later on. And we call these abundant minerals as silicates in the earth, because there are about 6 groups of silicates. You will learn about these minerals. It's purely mineral classification. So these silicates are composed of mainly silicon and oxygen, right, in the form of oxides by a silica, we call it a silica tetrahedron. That means SiO4 units. So these SiO4 units are combined with other metals, other elements like iron, magnesium, calcium, like aluminum, like elements, so that different different chemical compounds are formed. So these different chemical compounds are termed as minerals. Okay. Actually, not only silicates, but also other compounds are also there, oxides and barytes and hydroxides, like things also. They are less abundant, right? Silicates are the most abundant chemical compound in the earth, which we encounter as different minerals, different colored minerals, or different shaped minerals, depending on this the combination of this SiO4 unit. So you will learn about this silicate classification later on, because different hardnesses, different densities, different features are there. All depend on this, how this silicon tetrahedron is combined with other elements, and even some multiples of these tetrahedrons are interconnected, right? So depending on that, we have different minerals. So out of these how many minerals are there, in the earth? All these minerals, if you count them, any idea? Some rough idea? How many minerals? Can anybody tell?
Around 3,000 minerals?
Yeah, that's right. Around 3,000 minerals are there. But only 150 or 200 maximum qualifies as gemstones, as gems, right? Because they for a mineral to be called a gem, there are some specific features necessary. Otherwise, we can call all minerals as gems, right? But we don't do that, because beauty, durability, hardness, such special features are required for a mineral to be called gem. Otherwise, there is no economic value for those ones. And also some special geological conditions are required for these gems to be formed. Right? It's not easy to reach these special conditions. I mean, to make it a very durable one, very hard one. For example, diamond, right? The hardest one. You need some specific geological conditions, and also, for example, like sapphire, ruby, to form them, you need very special geological conditions. Not everywhere you can find rubies. We don't, in Sri Lanka, we don't find the diamond, right? But in Africa, where you have a lot of diamond, you don't see rubies and sapphires much, right? So because they are each place, some geological conditions are different. So with respect to the pressure and temperature conditions in the Earth's interior where these minerals were formed, if such special geological conditions are met, only these minerals can be formed. That's why they are rare, right? Not everywhere you can find. So that is one qualifier. There are some other very common geological conditions where you can see any place in the world quartz and feldspar, right? Because quartz and feldspar does not need these specific geological conditions. That's why you have a lot of quartz and feldspar, and also they are not they are not economically of a high value because they are everywhere, right? But ruby, sapphire, they are not found everywhere, and they have, in addition to that, they have very other important physical features as well. Therefore, we call them, we consider them as very valuable. Anyway, this chemical differentiation is an important feature, and this has taken place in the Earth at the very beginning, around 4.5 billion years ago. So first, you can see this accretion diagram. Accretion means the interconnection of these tiny materials, right? Some dust grains, some basically, so you can see they are very tiny scale, and they are kind of dumped into a field of gradually increasing gravity, because once you have these masses accumulated together, only you have a gravitational field formed. So then these materials are get accumulated. Actually, this accretion is a stage-wise process, as you can see here. So they can even collide physically, these materials, and also once these planetesimals formed by these tiny clumps of dust grains, they can collide, and then heat energy can be formed, right? So likewise, some energies, some energy fields also generated in the early Earth, early solar system, and due to accumulation of these tiny planetesimals together, they started to have a gradually increasing gravitational field. And once this gravitational field is there, it's easy for uh, other materials to be accumulated further and further, because once you have a gravitation, it's like you are a magnet attracting some iron particles, right? Once you have a magnetic field, it's easy for the materials or uh, iron powder like things to be accumulated into the magnet. So it's something like that. So under the gravity, once the gradually developing gravity, more and more matter can be accumulated there, right? So then these accumulations get bigger and bigger, and it forms into a material called a body called protoplanet. Okay, so this accretion also involves some collision and other internal activities in their collision in their accretionary process. So therefore, this formation of planetesimals is another in another way is a process of formation of heat, right? So therefore, some heat is also generated while these protoplanets are formed. So this is how the Earth's first heat energy was formed, and now these heat energy is getting accumulated or gradually increasing, because there are more and more protoplanets or planetesimals are formed in this system. So you can see the scale of these bodies. Some protoplanets are of 100 to 1,000 kilometer scale, right? And some planetesimals are some kilometer scale, even smaller. Some these very tiny materials of very millimeter or centimeter scale, they get accumulated and forms planetesimals of some kilometer size even. And under the gravity, increasing gradual gravity, they get interconnected and forms more and more bigger materials called protoplanets, right? So these protoplanets can be of some thousands of kilometers, and even these protoplanets can get into accumulated into themselves and make more bigger protoplanets. So that's how we had this Earth-like the big bodies could have generated, which could lead ultimately to different types of planets in the solar system. Right. So this is what you call the Earth's accretion process. Earth's accretion process, and this process is very important for Earth's formation, where we have a differentiated planet ultimately form. So this Earth's differentiation, until this time of differentiation, it has taken place about 4.56 billion years ago. So once this protoplanet formed and it started differentiation, at that stage actually is the birth of the Earth. Okay, birth of the Earth. Until that we don't have a planet, right? We had only a protoplanet, right? That is the time of the birth of the planet. Okay, so any question up to this content? Is there any question?
No, it's clear, sir.
Okay, so I hope everyone got it clear. So we will move to the next one then, next slide, that is about the chemical differentiation. So chemical differentiation, as I explained before, it's just after the formation of the protoplanet, then depending on the densities, the elemental segregation into different layers. That is what you call the chemical differentiation. So this it is believed and by scientists that it was completed by about 4.3 billion years ago. So that means it has taken about 200 million years. Do you understand that? This is like 4,300 million years, isn't it? The age of the Earth is 4.5 billion years. That means 4,500 billion years. So since that time, until completion of this chemical differentiation, that means the changing, the separation into layers of the Earth has taken about 200 million years. Okay, 200 million years it has taken place. It has taken to complete this process, where we could see a crust, mantle, and core. Actually, initially, first differentiation was the core differentiation, the most heavier things. So for this differentiation, it has taken place about, it has taken about 100 million years for the core formation, and then mantle formation, and some part of the actually crust was the late process, the last process. Basically, core mantle differentiation, it has taken place about 4.3 billion years ago, right? That means around 200 million years taken to complete until the mantle differentiation, right? Until a layer called mantle was formed. Just for the core formation, it has taken about 100 million years, right? So that means about 4.4 billion years ago, the core has completed its formation. So these are also understood by and also determined by isotopes, but not the uranium lead or some other the normal isotope. These events has been dated by tungsten isotopes. Tungsten, W, element tungsten. This tungsten is a very, because at this stage everything is molten, so their melting points and all are very, very high. So uranium lead are not feasible to analyze, to escape or to survive at that time, at that temperature. But tungsten isotopes has recorded some features of this early core generation, and they have contributed to determine the age of this core formation. Okay, right. So then after the core, the mantle was formed, slightly lighter than the core, but heavier than the crust. Okay, because the mantle contains a lot of iron and magnesium again. Most of the iron is concentrated in the core, and the magnesium bearing minerals, mainly the elements of magnesium was concentrated in the mantle layer. So we have a lot of minerals which are formed by magnesium in the Earth's mantle. For example, something called olivine, right? Olivine, it's a semi-precious stone, a semi-precious mineral, or in other words, uh, the peridot. Yeah, I think peridot. Do you? It's olivine,
Yes.
right? It's olivine, isn't it? So this is magnesium, pure magnesium. I mean, if it is an N member, I mean, it's a compositional variable between iron and magnesium. Some contain iron as well, but the N member, that means the purest olivine, is forsterite. We call forsterite. It's magnesium silicate. It's magnesium rich. So these magnesium bearing ones minerals are dominant in the Earth's mantle, plus some iron bearing ones as well, pyroxene like, right? So these pyroxene and olivine are the dominant minerals in the mantle. It contains only very limited amount of feldspars and quartz. Very limited.
Excuse me, sir.
Even no, yeah.
Yeah, this liquid iron outer core,
Yeah,
is normally liquid. Is it getting harder or it's remain as a liquid for a long time?
yeah. It's remained as liquid since the Earth's formation. Still, it's liquid. It does not get solidified because the pressure is not sufficient to make it solid iron there. It's still in the liquid state because the temperature is too high. So, but the pressure is not sufficient to make it a solid iron.
It will remain as liquid core.
Yeah, it remains as liquid core, and because of that liquid core only, there is possibility for that layer to be movable, right? It's like a gel-like thing actually. So it's still movable, but it's not a complete liquid. I mean, it's almost a liquid, but still it can be there as uh, what you call generating convection currents. It has positive possibility to generate convection currents, and that's the reason where we have a magnetic field as well, right? Not only, I mean, not only the solid core, but the movable liquid layer of iron also contributes positively to the Earth's magnetic field.
Thank you.
Right. So in the mantle, what you have is iron and magnesium. Magnesium is the dominant one. It is less denser than the iron and nickel bearing core. That's why it is lying above the core. So this mantle extends. You can see the length, from starting from 40 kilometers. If you start measuring on your surface, from your surface down into the Earth's interior, once you pass 40 kilometers, then you can see the signs of the mantle layer. Okay, until 40 kilometers, you might not encounter the mantle, and from there onwards, it will be the mantle, and then it will continue up to 2,890 kilometers depth. Okay, so it's a vast area, right? 2,890 kilometers, and from there onwards, you have the liquid iron core until 5,150 kilometer depth, right? Then you have the solid iron core, and the center of the Earth, until you meet the center of the Earth. Center of the Earth is about 6,370 kilometer. Okay, so that is the length if you measure from the surface about this layer. So you can understand now how thick these layers, right? Some uh, thousands of kilometers thick, right? So only the crust is very thin compared to these layers. So we think it's like a eggshell, right? The crust, the thickness is very little. That means it's a very thin compared to the other layers, which are some thousands of kilometers thick. So it's a tiny crust we are standing on the Earth, right? So that's why this tiny crust is easily breakable, like an eggshell, right? You can break them into pieces, right? So actually, it's already broken them into pieces, the crustal parts, and these crustal parts are moving relative to each other on top of the mantle, because the crust is lying on top of the mantle, and since this crust is fragmented, this crust is broken into pieces, they can have the independent movements. So because of some heat forces, these crustal fragments can be moved. So I think probably you may have been introduced about the plate tectonics, the concept of plate tectonics. Have you done that part already, or you are just got in an introduction?
Yes, sir, done.
Okay. So these plates means these crustal fragments, these the parts of these crusts. So these plates can be movable because of they are broken into pieces. The crust is broken into pieces. So that is what you call the plate tectonics. So anyway, our crust is there as a thin layer, which is fragmented also, and not only that, it is composed of two parts. One is ocean, and the other one is continents. So oceans, you have the ocean bottom, where we call that part as the oceanic crust. Okay, on top of the oceanic crust, you have the water, ocean water, sea water, right? Then you have the continents. So all these two parts are composed the crust. So in general, we call crust for the both oceanic and continental parts of it, right? So the crust can be divided into two, oceanic and continental, and then what you have the mantle, and then we have the core. Even the mantle can be divided into two parts as upper mantle and lower mantle, and then the inner core and outer core, like, right? Upper mantle and lower mantle. We'll see their differences later on. The crust is divided into two, oceanic and continental, and then mantle. It is divided into lower mantle and upper mantle, and the core is again divided into inner core and outer core. So these are the main layers of the Earth, and since they are composed of minerals, right? Different minerals, their properties are different. In the core only you have just the elemental forms, right? No minerals are there. They are elemental iron and nickel is there, right? They are not minerals. They are elements. Then what you have in the mantle, some iron and magnesium bearing minerals. After that you have crustal minerals, mainly iron, iron also there, aluminium, silicon bearing crust we have, right? Magnesium, aluminium bearing crust we have. So you understand now that based on their major mineral compositions, major elemental compositions, there are different minerals in these different layers of the Earth. So by definition of a mineral, what is the definition of a mineral? Do you know that? Maybe you haven't learned about it yet. The definition of a mineral is I mean, in very general terms, I'm going to tell you, it's just a combination of elements, right? It's a combination of elements with a fixed chemical composition, right? Elements are combined in fixed ratios so that a compound is generated. You can call it a mineral, which is formed naturally, right? A naturally forming chemical substance is called a mineral, where you have a fixed chemical composition, right? Because elemental combinations are different, so therefore you have different minerals formed in the Earth, right? Even iron, magnesium, aluminium, silicon, oxygen, These five elements can combine in different ways to form more than one mineral, right? So likewise, different minerals are formed, but in different minerals, same elements are there, but their proportions and their ways of combinations are different. So that's why we have different densities, different hardnesses, different colors. Likewise, some physical features are different because of those changes. Okay. Right. So I hope this basic concept you can understand clearly, because there is nothing much deep uh, deep chemistry or anything.
Yes, sir.
Yeah. Any question?
So in terms of total volume, which layer is the largest?
Well, the volume is different because you have some layers are confined, right? So I will give you all the dimensions later on, so that you can compare each and every layer in terms of volume, in terms of density, in terms of other physical properties. Okay. So we will. I will.
Do you share these presentations to us?
Yeah, later on I will share. At the end of the lectures, I can share, so you can get more as a reading material, this one. In
Okay.
addition to that, I will give you some additional materials also with respect to the other features, like what you asked now, volume and other physical properties. Okay, parameters. Yeah. Right. So as I mentioned, this is very similar to a egg, isn't it? Shell, you can equivalent. It's like equivalent to a crust. Egg white is like mantle, and then yolk is like core. Okay, but the inner core is dense. It's hard, right? So this is the dimension. Some of the dimensions with respect to the Earth, where you have this crust, mantle, and core. These are compositional layers. Remember, these are compositional layers. Why we call them compositional layers? Because their elemental compositions are different, right? As I mentioned before, their elemental compositions are different. So therefore, you can call it compositional layers. The crust, as I mentioned, you have the oceanic part plus the continental part. So always remember, this oceanic part is joined with the continental part. In the Earth, in the oceanic bottom, ocean bottom, you can see, if you can go there and see these features. Actually, it's possible. You can see these are interconnected, right? They are welded together. So this oceanic part is always thin. Remember, oceanic crust means a thin crust layer. On top of that, only you have these oceans, right? And then the continental crust is usually thick compared to the oceanic crust. But altogether, as I mentioned before, it's like 40-50 kilometers maximum, the average thickness, continental crust. But the oceanic crust is about 7 kilometers thick, right? It's not very thick, it's thin compared to the oceanic crust. Sorry, compared to the continental crust. But the places where you have these trenches, the subduction zones, the trenches, deep trenches. Mariana Trench. It's a part of the oceanic crust, right? But there, the trench is very deep, and also the crust is also a little thicker there. It can go up to like 11 kilometers or 12 kilometers, like the thickness in such special places. And also in the continental crust, the places like Himalayas, Everest, Mount Everest, up to the top of the mountain, from the base of the crust, thickness varies about 70 kilometers. So that is the thickest crustal part we have in the Earth's crust. Okay. The Mount Everest or the Himalayas is the thickest part of the crust. So because of these plate collisions, this Mount Everest or the Himalayas are getting more and more thickened and also uplifted. It's getting more and more uplifted. They are making a very thick crust. So such special locations, we call them collision zones. We call them collision zones because there are two continents are colliding there, right? Maybe under plate tectonics you have discussed these ones. Probably if we have time, I can also explain you a little bit more regarding the details of those, and also about the subduction zones. Subduction zones means like Mariana Trench. These are the some specific places where you have these unusual thicknesses in their crustal regime. But the average thickness, if somebody asked about the average thickness of the continental crust, you can generally tell them it's about 40 to 50 kilometers, like, right? In average, actually, it's 40 kilometers, most of the places. That is the most abundant thickness, 40 kilometers. The oceanic crust is about 7 kilometers. That is the average thickness. Okay. So then you have after the this crustal layer, what you have is some kind of a boundary. We call this boundary moho, M-O-H-O, moho layer, right? This is a moho. It's actually derived after a name, right? The person who was studying about this structure was his name was Moho. Therefore, it is called Moho layer or Mohovic discontinuity, because this is a kind of a discontinuity. That means you can't continuously see the properties of crust there because it's a transitional layer. Actually, it's a transitional layer in between crust and the mantle, because from there onwards you have the mantle. Okay, from there onwards, from after this layer, what you have is a mantle, right? So it's something like here, this layer, very tiny place, right? So we call it a discontinuity layer. That means the features or properties of physical parameters are not continuing from there onwards. So therefore, it's a boundary layer. We call it Moho discontinuity or Moho, just Moho, because there are a lot of changes are happening physically and chemically within the Earth's interior. And also this has been detected not by just digging into the place, because you know it's 50 kilometer or 40 kilometer beyond there, right? You can't drill any borehole up to that depth. It's it's not possible. So therefore, indirect methods have been applied to understand the internal structure. Actually, these are understood by seismic waves. Okay, so the propagation of the seismic waves are disturbed at this length, at this depth, 40 kilometer depth. Most of the places in the Earth, this disturbance has been observed, and therefore people were curious to see what is going on there, right? Because there is a reflection. Seismic waves are reflecting backwards. S waves are reflecting backwards mainly because of not only X waves, P and S both, because the features are different, and also the velocities are changing. The P and S wave velocity, seismic wave velocities are changing from there on. So that indicates some special layer is there. So then only people understood that the properties are different there, because there are a lot of melting is taking place in that region. A lot of melting is taking place. I mean, the magma generation and other things are happening. So the features are different in that particular part. So that part is all over the mantle. So therefore, that layer is called Moho layer, right? So in between the mantle and the crust, we call the separation layer of mantle and crust as the Moho or Mohoic discontinuity. So From there,
I have a small question. It's not directly connected to this. Like we are studied about like metamorphic system of gemstone formation and this volcanic system.
yeah,
Right. How does it vary from one place to another place? Like some places, like you get always a metamorphic system gemstone formations, and other place like volcanic system.
yeah.
What's the impact from the earth to have a different kind of formation systems in the same earth?
Yeah, actually, it's mainly dependent on the physical parameters. Okay, what are the physical parameters we have in the Earth which affect the metamorphism or volcanic systems or formation of minerals? Because metamorphism and volcanism are the main processes of generation of minerals, right?
Yeah.
Yeah. So actually, the physical parameters means temperature and pressure. The temperature and pressures are changing in the interior from place to place. So at different places, different grades of metamorphism or different extent of volcanism is magma generation is taking place. So based on that, these activities are different from place to place. Not only that, the forming magma is also different, chemically different. Not everywhere the same magma is generated. So the chemical composition of these magmas are different. Some magmas we call alkaline magma, some magmas we call felsic magma. Likewise, there are different different chemistries available. So based on that, and the physical parameter control is there, the pressure and temperature differences are there.
Yeah.
So based on those, these all formations are different. So you will learn about this, I think, in the lectures to come. These differences. Yeah, I will also cover up some parts later on.
Okay, thank you.
Yeah. So, yeah, this Mohoic discontinuity makes the transitional zone in between the crust and mantle. Okay. So then after the moho, you have this mantle, that is the upper mantle part. Upper mantle part is there. So it is mentioned as mantle here is as a single layer, but actually, as I mentioned before, the mantle itself has two chemistries. That's the main reason. Not only chemistry, some physical parameters are also different. Okay, physical properties are also different. Upper mantle is different from lower mantle. We will learn about these differences in detail with the progressing of the lecture. Okay. So first we have this continental crust, oceanic crust together joined at a single place, at one place. And then so you can just think of a beach, right? So when you go deep into the ocean, somewhere you will meet the oceanic crust. Okay. So this oceanic crust is welded with the base of our continent, right? Always this is welded together. It's a very heavily welded. I mean, it's not easy to detach. It's not easy to detach, but only possibility is being this oceanic crust has a different composition than the continental crust. So as I mentioned, their elemental distribution is different. Oceanic crust is always having like a mantle-like composition. Like, I mean, it's not equivalent to the mantle, but iron and magnesium is rich there in the oceanic crust. Mainly iron is dominant than magnesium there. In the mantle, you know, it's magnesium is dominant, but the oceanic crust also contains a considerable amount of iron and magnesium. So therefore, the minerals formed in the oceanic crust is different from the minerals formed in continental crust, because in the continental crust, what you have dominant is aluminium, calcium like thing, right? Yeah, actually, calcium is also there in the oceanic crust also, but you can consider aluminium is dominant in the continental crust, and iron and magnesium is dominant. Iron, magnesium, and calcium is dominant in the oceanic crust. So therefore, the mineralogical terms, oceanic crust is heavily composed of iron, magnesium, and calcium bearing minerals, whereas the continental crust is mainly composed of aluminium rich minerals. So aluminium rich minerals are less dense. For example, potassium feldspar, K feldspar, quartz. Quartz is entirely silica, right? No aluminium even. So these are less dense. So therefore, continental crust is less dense than the oceanic crust. So oceanic crust is heavier. Always say oceanic crust is heavier. So in such a situation, when these two ocean and these two crusts are meeting together, right? If the plate tectonic permits, if the plate tectonics pushes this oceanic crustal fragment against the continental fragment, because all depend on the convection currents which are available in the mantle. Convection current means the heat transferring mechanism, one of the heat transferring mechanism. We will see them detail later on. Since the oceanic crust is pushed against the continental crust, what is happening there is, being this oceanic crust is more dense, it tries to subduct beneath the continental crust. The heavier one tries to go beneath this ocean continental fragment. So therefore, most of the cases, this oceanic crust tries to subduct beneath this continental fragment. So that's why you have some subduction zones generated in some parts of the Earth. Okay, so if the plate motion pushes this way, this oceanic crust can collide to some extent with this continental crust, and later on, because of its heavy density, it can sink down into the interior. It can sink down into the interior. So therefore, such processes are taking place at the margins of oceanic and continental crust. And in the same way, there are some places where this oceanic crust is moving away from each other, right? When this ocean crust tries to move away, I mean, if the convection current is forcing like this direction, so then oceanic crust tries to go away from this continent, okay? Because it is attached to the continent and it tries to remove the attachment. And then what happens when it tries to remove their bonding? Some fractures are generated in this region. Some fractures, that means it tends to fracture. Okay, it tends to fracture because of the tension, because of the tension applied beneath that plate. So it creates some tensions and it expands these tensions, and once you have a opening there because of this expansion of tensions, magma which is lying down there in the interior, because magma is there always everywhere in this region in the mantle, so that magma tries to rise up. Okay, so once you have a fracture here generated, this magma tries to rise up and dump on the ocean floor, right? Magma comes up and uh, and eruption is taking place, right? Eruption is taking place under the sea, under sea. Okay, the ocean water is here, the eruption, magma eruption is there, right? It's not like a normal volcanic eruption where we see it in a continent, right? In that case, here you can see clearly a volcano, right? But in this case you can't see the volcano because it is hidden there by the ocean water. So therefore, we call it underwater volcano. And these volcanoes, by dumping materials from the Earth's interior, generate some kind of a mountain-like features even under the water, right? So these mountain-like features which you have in the oceans are called mid-ocean ridges. Mid-ocean ridges, because these are also like ridges, like mountains, right? But they are underwater, right? But these mid-ocean ridges are extending linearly to very long distances. Okay, so every ocean has some this type of ridges because of these tensional forces, which creates initially some fracture in the oceanic crust, and then with the time this fracture expands and continues. The eruption is also continuing, where you see different magma episodes are dumping materials, right? These are called magmatic or the mid-ocean ridges. In the inside of the ocean, you have the volcanoes produced. So this type of structure you have in the oceanic crust, and simply the continental crust is just some groups of mountains or some plateaus or some uh, some geomorphological features that you see on the surface. All these are composed as the continental crust. So since I mentioned that there is some plate motion or plate activities taking place in the Himalayan region, day by day Himalayan region is getting uplifted, getting elevated. It is the mountain height is getting higher and higher, very little amount, actually some millimeters, but it is taking place throughout the history. And now it has come to a certain situation where the maximum compression is there. So actually in the near future there can be some fracturing happening there as well because of the compression. It's not tension, it's compression. Okay. Because it's like you are pushing something against a wall, right? You are compressing that, right? So it's like if you have a balloon, if you can push it over a wall, and at a certain time when it reaches its maximum compression, it will explode, isn't it? So likewise, these crusts can be also fractured, exploded. That's why actually even now you can see some earthquakes in the Himalayan regions, nothing to do with any subduction like things which are happening as usual earthquakes in Japan or Indonesia. So this type of structure is there in the crust. So this is also very important, and also the processes are taking place, magma generation and different processes. As I mentioned, one as an answer, I mentioned about the chemistry of magma, right? So these are the differences in chemistries of magma, because continental fragments have different chemistry than the oceanic fragments. So the magma generated in the ocean part is different from that generated in the continental segments, right? In the continental segments, you have more silicic magma. That means more aluminum rich, silica rich magma. But in the ocean part, you have a lot of mafic minerals. Mafic minerals means iron, magnesium rich minerals. So there is something called mafic and felsic. Okay. Felsic means silica and aluminum rich portions we call felsic magma. They are light colored, right? You see quartz and feldspar, they are light colored, right? That's the reason. But if you see olivine or pyroxene, they are dark colored because of iron and magnesium enrichments there. So so magma being generated out of them is also different in chemistry wise as well. Okay. So anyway, these cause different minerals to be formed, and in any case if these minerals meet those required requirements, essential requirements, what you get is gemstone forms, right? Gem minerals form. So likewise, it's not common everywhere. The chemistry is different, the physical conditions are different, and also not only just the chemistry, but also the physical conditions are the main reasons for these different minerals to have different genetical environments, the pressure and temperature conditions. So when it comes to a depth of like 40 kilometers, the pressure is like 10 kilobars. Okay. So the minerals formed at 10 kilobar, maybe at that region the temperature is like 700 or 800 degrees Celsius at that depth. So physical condition is that at that depth, but at a shallow depth it's different, right? The maybe the pressure is like 5 kilobar, temperature is like 500 600 kilobars, Celsius. So the minerals which can form, actually the minerals which are stable under that pressure and temperature range is different from those which are stable under more higher pressure and temperature regions. So therefore, we can see the vast combinations of minerals formed at different places, and that applies to the gems also, right? Those are very different. And for example, for gems like diamonds, they need very high pressure conditions, very high pressure conditions needed. So they prefer to form in subduction zones, because subduction zones means the places where these rocks are subducting into deep interior. Something is going deep interior means you are increasing its pressure gradually and continuously. So it's a favorable situation for diamond to form. For example, the graphite. Graphite is carbon. Diamond is also carbon, right? But graphite is available in this region. In our continental crust or in our country, in rocks, we have a lot of graphite, but we don't have diamond, right? But if our rocks can be buried into that depth, this graphite will be converted uh, into more denser carbon variety, that is diamond, right? So that is possible. That's why we mentioned that some specific geological conditions are required to for these gems to be formed. Even for rubidium, for ruby and sapphires, the story is same. We have a lot of ruby and sapphire, right, in our crust, in our rocks, because all these gems you find in Ratnapura are uh, products of rocks. They were found in rocks some million years ago. Now they are eroded and deposited in river basins, paleo river basins. You are excavating a gem pit means you are excavating a paleo river, some river long time back, right? Some million years ago, some river basin you are excavating, right? You are mining. So these gems have a special property as durability and hardness. They are not decomposed into soil. All other minerals decompose into soil except these gemstones, right? Because they are harder. Zircons and others, sapphire, ruby, and other gems you have in a mine are remaining there because they are hard. They have a special property. So otherwise, they were all together formed like feldspar, quartz in some million years ago. So all these uh, quartz, feldspar, hornblende like minerals formed together with those gems, ruby, sapphire, are all decomposed into soil now. But those are the other things are remaining there as gems because of those special properties. Okay. So anyway, different chemistries are required to form these different minerals, and that is available with respect to the structure of the earth that you can consider all around. Okay. So so compositional wise, you can divide the earth into crust, mantle, and core. And then there is another classification where we consider rheological differences, rheological or in terms of mechanical properties. Okay, some of you may be familiar with these mechanical properties. That means the strength of the rocks, right? How hard these ones. I mean, as a rock, not as a mineral. Hard, not hardness. I'm referring here hard, right? How these rocks layers behave under applied force, right? Once you compress them, once you make tensile or subject to tensional forces, how they behave. Some rocks may be just fracture and remain as it is, but some rocks may be even undergo powdering, right? Some into fragments, tiny fragments. They can break into tiny fragments. Okay, so that can also be there. Those are different mechanical properties depending on. So we call them geologically or structural geologically or even tectonically as the rheological features. Rheology means how their mechanical features are different in different rock types. So these are rheological features, and based on that, these rocks, these layers, the earth can be again defined into some layers. So that those layers we call lithosphere. That means a sphere. It's a circle because these layers are circular in the globe, in the globular, right, in the planet. So therefore, spheres, as spheres, you can mention because if you mention one layer, it is circular, right? It is continuing all over. So therefore, it is in 3 dimension. You can call it a sphere, right? This is a sphere. It's not a simple circle. So lithosphere, asthenosphere, and mesosphere. These are the 3 layers we consider in in the Earth in terms of rheological differences. So you have this asthenosphere as the lithosphere as the closest layer. Lithosphere, if you take a section like this, right? Lithosphere is the very shallow region, right? So starting from the surface, you can continue up to the moho like, right? Up to this level like. So all the crust is included there, and also a part of the upper mantle is included, because from there onwards mantle I mentioned, right? So this mantle is also defined as lower mantle and upper mantle. So up to the upper mantle part, starting from the crust, starting from the surface, you can continue up to the upper mantle region, and that part is called lithosphere. So that means it's not a single crustal section. It concludes the part of the mantle as well. So that's why we define it in a different term as a lithosphere. Litho means it's a Greek term used for rocks, right? It's a litho means rock. So it's a rocky layer actually, right? In the upper part of the mantle, until the upper mantle layer, all these rocks are solid, rigid, right? But from upper mantle downwards, this rigidity changes. This all of course they are solid, but this solidness changes. Okay, so some part of the mantle starts to become it's not total liquid but not total solid as well. It's something like gel-like feature. So until that, I mean jelly, you can see jelly, it's a movable. I mean the materials are moving, but it does not flow, right? If it is flowing, then you can call it a liquid, but it's not a solid as well, right? So it's a semi-solid like, right? So therefore, until that depth, everything is solid. That because they are composed of very rigid rocks, solid rocks, and that part is called lithosphere. So that section you can term like this. So see here, the most shallow part is termed as lithosphere. So this lithosphere contains the crust and the upper part of the mantle, and then comes asthenosphere. Asthenosphere is mainly the mantle part, uh, except for this the exterior part of the mantle, the exterior upper part of the mantle, until the lower mantle section. You can call it asthenosphere. Okay. I mean until the upper part of the mantle, right? Not the entire lower mantle, upper part of the upper mantle, upper part of the upper mantle, right? Because you have the mantle, lower mantle, upper mantle. Sorry, I think I mistook. You have the upper mantle and then lower mantle, right? So the lithosphere is composed of crust plus upper part of the upper mantle. Okay, the uppermost part of the upper mantle, and then from there onwards you have the asthenosphere. That means upper part of the upper mantle, and then you go down to the lower mantle region. In the lower mantle, until the upper part of the lower mantle, you have this asthenosphere. Okay, so the lithosphere is here, and then asthenosphere is here, right? Then what you have is mesosphere. So this mesosphere is entirely composed of the lower part of the lower mantle section. We call it mesosphere, but from up to the outer core, right? Up to the outer core, because the outer core is just the liquid. Metals are there, iron and nickel bearing metals, because there are no rocks, no minerals. Therefore, the mesosphere stops there in the in the uh, in the core boundary. Okay, so this is actually this classification, this rheological classification is mainly based on the the rigidity of these rock units, and the crust mantle core differentiation is mainly based on the composition. Okay, so compositional layers and rheological layers are the two types of layers. Actually, they are part of each other, but depending on the usage, we can opt into whatever the type you need. If you want to describe the in compositional layers, then you have to talk about the crust mantle core. Otherwise, you can call about the rheological layers. Okay, so is it clear up to this point?
Yes, sir. One more small question, like we have studied about these the plating systems of the uh, uh, plating systems where we remember like Tatibulgar, Kalpite. Is that plating system is in the crust, right?
Yeah, definitely. The plates means always the crust. We refer only crust. That means crust. Actually, the plate. The definition of the plate is the crustal segments, crustal fractions, because there is possibility for these crustal fragments to float. This floating is taking place on top of the mantle, right? On top of the mantle, because the uppermost part of the mantle is sort of flowing like semi-solid like. That's why I mentioned it's part of the asthenosphere. Okay, so uppermost part of the mantle is flowing. So this crust plus actually the lithospheric plates. If you use the lithospheric plates, that is the most uh, suitable explanation, because the lithosphere contains a rigid part of the mantle as well, right? So the crust is attached to that part, and that part together floats on the this semi-solid part of the mantle. Actually, mantle is semi-solid. That's why it has the ability to float. So these plates are moving. That means the most exterior part of the lithosphere. I mean, entirely the lithosphere you can consider as a plate. That's no harm.
Okay.
Yeah. Any question? Anyway, we will continue with more descriptions later on about the structures. So for today, I think we can stop here, unless you have any other clarifications or questions.
It's okay. I think the presentation nicely done and it's very clear. Very clear.
Yeah, I will give you the details. I mean the slides even later on. Once I complete some parts, so part by part I can give you. Okay. Yeah. Okay. So if you don't have any more questions, anyway, if anybody has questions, you can post it now. And I hope everyone typed your name and put in the chat box, right? Because that will record as your attendance.
So do you mind to share your contact number if you want, or
Sure. Yeah, no problem.
to
If you
get
can,
more idea?
yeah, if you can take it down, I can just tell you now. It's not
Yes.
71.
Okay.
Not 71 868.
Okay.
2715.
715. Okay.
868-2715. So I might not be always answering, but you can drop a message. Okay.
Right.
So then I can call back.
Okay.
Okay.
Thank you.
So then we will stop here for today, and so we will see next time.
Thank you very much.
Okay.
Thank you, sir.
Thank you, sir.
Thank you.
Bye.
Thank you, sir.
Okay.
Thank you, sir.